Hi, my name is Tiffany Callahan. I am a PhD candidate at the University of Colorado's Anschutz Medical Campus, advised by Drs. Michael Kahn, Larry Hunter, and Tel Bennett. I'm excited to present to you today some of our recent work building open source software to construct biomedical knowledge graphs. In the United States, the adoption of EHRs is now nearly universal, providing researchers with the data they need to start developing smarter healthcare systems. Smarter healthcare systems means more intelligent use of existing data, but also smarter experimental design and algorithm development. So how do we do this? That's a question we've been trying to answer in my labs. This figure provides a high-level overview of my vision for creating smarter healthcare systems. It highlights 3 projects, each designed to improve the integration of biomedical knowledge with patient clinical data in order to enable more complex and intelligent analytics. Today's presentation will focus on Phenolator, open source software designed to make it easier and faster to build large-scale heterogeneous biomedical knowledge graphs. Phenolator is designed to help solve one of the biggest issues preventing smarter healthcare systems, the fact that most medical records are not easily connected to biomedical knowledge. We demonstrate what we mean on the following slide. Currently, researchers are able to use medical record data to do things like perform real-time detection of patients most at risk for rapidly deteriorating, automatically triage patients based off of their medical conditions, predict pertinent patient risk factors, and identify emerging or important pathogens like COVID-19. But by connecting medical record data to biomedical knowledge, we will enable better integration of patient omics data, identify causal biomarkers, and be able to generate mechanistic explanations for observed patient characteristics, as well as more easily integrate relevant environmental exposures and social determinants of health. Knowledge graphs provide one strategy for connecting biomedical knowledge with clinical data. They are frequently used in biomedical research because they can represent complex biomedical relationships and enable the integration of heterogeneous data. And many knowledge graph construction methods exist and include everything from domain-specific manual to fully automated approaches. But there are many challenges to building and using biomedical knowledge graphs. First, there are significant design challenges due to the multiple ways that one can model knowledge, which ultimately impacts the types of downstream learning one can perform. There are also significant implementation challenges. Opting for a representation that enables high semantic expressivity comes at the cost of significant compute resources. And some of the existing tools, while providing exceptional performance, are written in less commonly used programming languages, which makes them difficult to adapt, expand, or use. To account for these challenges and accommodate multiple users' needs, we've developed Phenolator, a novel Python-based framework to build and evaluate a wide range of large-scale, heterogeneous biomedical knowledge graphs. So let's dive right into how Phenolator works. Phenolator builds knowledge graphs in 3 steps: downloading a list of data, transforming the downloaded data and assembling it into an edge list, and then integrating the assembled edge lists with the ontology data sources into a biomedical knowledge graph. To complete these steps, Phenolator requires 3 input documents: a list of ontology URLs, a list of non-ontology URLs, and a file with ETL instructions including needed filtering and/or identifier mapping. To make this process easier, we provide a script that automatically creates these documents for a user. Phenolator outputs data in several formats. Knowledge graphs can be output in RDF XML, and triples, as a network-X multi-digraph, or as a text file of integer or identifier labeled edge lists. For ontology and non-ontology data, node metadata, including labels, descriptions, and synonyms, are output to a text file. And we'd also like to note that Phenolator provides functionality to add node metadata from non-ontology data sources directly to the knowledge graph as well. To ensure reproducibility of a phenolator knowledge graph, a text file describing all downloaded data sources and the performed transformations are also output. Finally, extensive error logging is performed throughout the knowledge graph construction process, and all identified errors are output to text files. And in order to meet a wide range of users' needs, Phenolator provides several hyperparameters. Firstly, we provide flexibility in knowledge graph type. So knowledge graphs can be constructed from scratch, or existing knowledge graphs can be processed through the pipeline. When building a knowledge graph from scratch, we provide two different approaches for uniting ontology and non-ontology data, which are demonstrated in this table using simple examples. On the left side of the table, we present and describe to you the instance-based approach, which is arguably a more common approach and the one used to construct things like GoCams. On the right-hand side is a subclass-based approach, which is the approach that's used to build the knowledge graph kebab. As you can see from this table, the subclass-based approach generates more triples, which means it will create knowledge graphs that are significantly larger than the instance-based approach. Phenolator also provides flexibility in how relations are modeled when constructing edge lists. As shown in this figure, there are three ways relations can be handled, using, as shown on top, a single relation with no modifications, as shown in the middle of the figure, a single relation and its inverse, which can be inferred directly from the relation's ontology. And finally, as shown on the bottom, for all interaction type relations, edges can be inferred to ensure an edge set is symmetric. Finally, there's an option in Phenolator to convert a semantic knowledge graph into a property graph, which provides users with more flexibility in the types of downstream learning they can perform. Currently, we provide the OWLNets method, which losslessly removes all of the OWL semantic triples to create a network which includes biologically relevant nodes and edges. A simple example of this transformation is shown in the lower right figure. The network on the left in this figure represents a semantic knowledge graph built using OWL, and the one on the right shows the network after it's been run through OWLNets. As you can see, the resulting knowledge graph is significantly smaller, but still contains the biological entities of interest. To evaluate Phenolator, we aim to compare the costs and benefits of alternative knowledge graph designs and implementations by leveraging both qualitative and quantitative evaluation strategies. For the qualitative evaluation, our goal was to identify similar biological knowledge graph construction methods and to compare them to Phenolator. To do this, we queried the GitHub API using a combination of 31 different keywords, as well as examined recent knowledge graph review articles. For the comparison, we extended an existing software infrastructure evaluation survey, which included 45 questions organized into 5 criteria. Those 5 criteria are listed in the table shown on this slide. Through this process, we were able to identify a total of 1,907 biomedical knowledge graph construction repositories, of which 14 were eligible to be compared to Phenolator, and of which are chronologically presented in the figure on this slide. For the first criteria, knowledge graph construction functionality, which aims to determine how much functionality each of the methods provide to support the building of knowledge graphs, we found that 12 methods provided code that automatically downloads a list of data sources. 9 methods were able to build multiple types of knowledge graphs. 1 method was run through the deductive logic reasoner ELK in order to confirm the consistency of the knowledge graph, as well as to generate new assertions. 5 methods provided functionality to process free text data sources. And a separate 5 methods provided functionality to process different types of clinical data. For the maturity criteria, which aims to compare the methods on their level, stage, or developmental phase, we found that the average number of commits made to the included repositories ranged from between 17 to 1,000 per year, and that over half the methods implemented unit testing and some form of continuous integration, And finally, that just under half of the methods provided explicit collaboration guidelines. In terms of the availability criteria, which aims to compare the methods on the ease of obtainment, we found that the majority of the methods were primarily written in Python, Java, and R. And interestingly, the highlighted figure demonstrates how the trend in programming languages used for building biomedical knowledge graphs has evolved over time, starting from being primarily Java, to a mixture of Java and Python, to now mainly being Python. And all but one of the methods was licensed, with the top two most popular license types being MIT and GPL. For the usability criteria, which aims to compare the methods on how easy they are to use, all but one of the methods was found to provide sample data. All but two of the methods utilized a literate programming tool or resource, and 60% included a recent knowledge graph build that depended on some form of restricted data source. For the final criteria, reproducibility, we found that 73.3% of the methods provided a tool or resource that enabled a reproducible workflow and eased the installation or run process of using the method. 6 of the methods utilized Docker, 3 utilized a Jupyter Notebook, 1 utilized R Markdown, and 5 methods were made available as a PyPy or CRAN library. For the quantitative evaluation, we worked closely with a PhD molecular biologist to design a knowledge representation, shown in this figure, that modeled human mechanisms of disease. And in this figure, ontologies are shown in gold boxes, as well as green edge labels, and the edge data between them comes supported from 2 experimental datasets and 22 linked open data results, resulting in a total of 34 unique edge types that are added to the ontology data. This knowledge representation was used for all of the quantitative evaluations that will be explained throughout the rest of this presentation. Currently, Phenolator can build 8 different kinds of knowledge graphs by varying the construction approach, shown in blue, either instance or subclass based, by how relations are modeled, shown in green, either using a single unmodified relation or by inferring inverse relations and ensuring that interaction type edges are symmetric, and finally, by whether or not owl semantics are decoded, which is showed in this table in pink. And as you can see from the numbers in the table, the knowledge representation on the prior slide resulted in knowledge graphs built ranging from 13 to 86 million triples with around 1 million classes. This slide shows the computational performance of the 3 different build steps across the 8 different knowledge graph builds. The top 2 plots show the average runtime in minutes, and the bottom 2 plots show the average memory use in gigabytes. The plots on the left represent the results for the instance-based construction builds, and the plots on the right show the subclass-based construction builds. So on average for step 1, which was the step used to download ontology and linked open data, it took about 5 minutes and used less than a gigabyte of memory to complete. For step 2, the data transformation and edge creation step, the average runtime was 21.86 minutes, and the average memory used was 2.11 gigabytes. Finally, step 3, the knowledge graph construction step, took an average of just under 6 hours and used nearly 36 gigabytes of memory. As one might expect, the instance-based builds were the quickest and least memory-intensive. In contrast, the longest, most memory-intensive build was the subclass-based approach when modeling inverse relations and decoding owl semantics. And it's important to note that this evaluation was performed without parallelization, although it can be run in parallel, in order to model the expected performance in a typical computational setting. The final step of our evaluation, which is currently in progress, will generate node embeddings from the different knowledge graph builds using a 2-phase graph representational learning framework. Each of the selected methods will emphasize a specific aspect of our knowledge graphs that we find important, including heterogeneous node types, hierarchical relationships, and multi-community node participation. Once the embeddings are complete, We will evaluate their biological utility on several different tasks, including node classification, link prediction, semantic clustering, biological analogical reasoning, and community detection. And these results are very important as they will provide some context to the usability of the different types of knowledge graphs that Phenolator can build. Being able to compare the performance of the different knowledge graph builds on these biological tasks will ultimately help a user better decide which build is best suited for their use case with respect to knowing how long it takes and how much memory is required to build these different knowledge graphs. And in conclusion, we've developed a framework which provides complete customization for building biomedical knowledge graphs and is fully done in Python. While our evaluation is not yet complete, our performance evaluation results are promising, and preliminary results from outside applications using Phenolator have highlighted its usefulness for building hypergraphs as well as performing toxicogenomic mechanistic inference. And we'd like to note that once our evaluation is complete, we will make Phenolator available as a PyPy library in addition to a Docker container that is pre-built. So finally, I'd like to note that none of this work would have been possible without the support of my co-authors and all of our great collaborators. And this work is funded by a training grant from the National Library of Medicine to the Computational Bioscience Program. And thank you so much for your time today. I look forward to your questions and your feedback.